in this second example of statically indeterminate torsion, we've got a very similar situation as we had with the first one. That is, we have an aluminum shaft, a steel shaft, but instead of them being coaxial in the sense of being all together at the same location, in this instance the steel is out here at the edge and we have solid aluminum. Hence the J, or pole moment of inertia of aluminum here, is just pi over 2 to the fourth or 8 pi. That for the steel is pi over 2, and so that's a little bit different. And also mathematically, the fact that these aren't all together in the same length but are separated is going to get handled in a slightly different kind of way. So let's do a free body diagram again around that central point. And in this case, when we do that, we see the aluminum here, we have the steel, a little smaller piece, and now carefully let's draw in a couple of things. One, we've got curl that gives us a right hand torque at 100-inch kips. That also makes us different than T3.1 where we had 120-inch kips. Now we got to use the outward positive normal for our unknowns. Even if we can guess which direction they want, if we want to be really precise about this, we need to use outward normals. Positive outward normals as our way that we work through the signs. And so now note what's going to happen here. There's our positive direction. We'll take in our equation for the sum of torques, get minus TA plus 100 plus TS, set it equal to 0, or this time what we get is that TA minus TS is equal to 100. Last time it was TA plus TS equal to 120. And it might seem a little counterintuitive, and that might turn out to really be the case. We're just being a lot more careful about the sign convention here. We're also going to do this a little bit different than we did with a relaxed reaction. Instead, look directly at our displacement compatibility, where since we know that these two shafts are joined at the middle, they got two fixed ends, one at either the far ends, we know in this case it's a little bit different than before, but that our twist in segment AB, although it's the same, it's actually opposite sign-wise of the segment BC. That's because with B, if it were rotating, and we could be correct, top is going to come towards us and it follows the 100-inch kips. That would be a positive rotation for AB, but that would actually be relative to from B to C. That would be opposite of the sign convention, right? Remember, for positive, as we move from left to right, the right side goes in this manner that you got seen here before. But if we flip that, if instead the end on the left is the one that sort of advances forward, that would be the negative direction. And that's going to mean everything for us here as we go into the force deformation relationship. Let's put this all in one step here. And TL over JG being the critical one. This is the aluminum, so TL over JG for the aluminum. There's a minus sign now, TL over JG for the steel. So note how that will end up working out. That minus sign will come in here and flip something to make that make a lot more sense, that they both are resisting the 100-inch kip-inch torque, that is. Right? And so what we get out of that, of course, is that TA now is equal to the opposite of the ratio of the two polar moments of inertia times the ratio of the two shear moduli, and then we've got the lengths are in the opposite direction. They turn out to be the same, of course, in this case. And that's all times T sub S. And this will be a little bit different from example T3.1 in the numbers because the aluminum changed slightly. So we have minus 8 pi over 2, and then there's our 4,000 KSI over 11,200 KSI times TS, and we get as a number there then effectively 16, the pi's go away 2, times 4,000 divided by 11,200, or minus 5.714 TS. My calculator, I don't have the minus sign there. And so now when we go and solve for our various torques, going back to the equilibrium equation, we have minus 5.714 minus 1 times TS. I factored that out, set it equal to 100. And our TS equals a negative 14.89 kip inches, opposite of what is shown, which makes a lot of sense. You'd think both of those would oppose the applied torque. And then we go look at our torque in our aluminum. That 14.89 will be multiplied by 5.714, a negative 5 point, so we get a positive 85.10 kip inches. So obviously the 89 maybe should have been rounded up one more digit. I might have neglected to see that. Just rounding error in there. And now we can just apply the torsion formulas for the max shear stress in each segment. We'll have then that tau max in the aluminum equals TC over J of the aluminum, so that's 85.10 kip inches times our distance to our outer radius, which is 2 inches, divided by our J, which is 8 pi inches to the fourth. And so times 2 divided by 8 divided by pi, and we get 6.77 KSI. So within rounding error of the supposed answer of 6.8. And then we have tau max for the steel, TC over J for the steel, and that's a negative 14.89 times 1 inch over pi over 2 inches to the fourth. And we get a negative 9.48 KSI, again within rounding error. The signs don't have particular physical significance to us, other than it gets things set up in the right way, the way it's supposed to really be working. But from a material strength standpoint, it's not going to initially have much of a direct impact for us. So we're pretty close here. You might ask the question, what you assume that you had a solid aluminum shaft. What if that were aluminum? Well, if it were truly aluminum with the distances involved, we should get exactly the same answer that we had in example 3.1, with the difference that we have 100 kip inches instead of 120 kip inches. And so straight linear ratio will actually give us significantly different numbers here. So it is the case that that is solid on the left. And we just have some sort of, actually I think these are that we just calculated are good, that the ones that are the so-called answers are the ones that are just slightly off, unless of course someone finds some small little error that I neglected to pick up on my own.